Hello and welcome back. I am Dominic Clevey of Central Washington University. Today we continue our study of logarithms by learning to solve equations and inequalities using logarithms. In some sense, today is fairly easy because we take something you've been doing since junior high school, solving equations with x's. We take something that we've been doing for a few days together, using logarithms, and simply put them together. There will not be much new mathematics today, but simply new ways of using the mathematics. And let's see what we can do. Solving equations, of course, is our goal. Solving equations has been a popular topic for us ever since we started algebra. And I will also tell you that the same big idea here is the big idea we've had for the last few days. When in doubt, what should you do? When you fall asleep in class and wake up and don't know what to say, what should you do? The answer is, we'll call this the best method. It doesn't always work, but it usually does. Take the log of everything. Take the log of everything you see and hope things magically get easier. One of the surprising things about logarithms, even though they're difficult and confusing at first, is that when we take a logarithm of everything, they often do get easier, and perhaps I should stop telling you this and simply show you one. Let's start immediately with an example. Our challenge here is to solve 4 to the power of x is equal to 3 to the power of 2x plus 1. Is there some x that makes this equation true? Well, there almost must be, right? We certainly believe it should be there, but finding that x seems really tricky. We saw a way to do some problems like this in previous sections. If this had been a 2, for example, we might have taken advantage of the fact that both of our bases are powers of 2 and rewritten the equations that way. There's an easier method, and logs will come quickly to our rescue here. What do? We take the log of everything. Which log? Any log will work, but how about the natural log? It's easiest to write. You only need 2 letters. It's beautiful. It's easy to find in your calculator, so let's do this. The natural log of 4 to the x, if this is truly an equation, must be the same as the natural log of 2 to the 3 to the power of 2x plus 1. We have laws of logarithms that tell us what to do with powers. The powers pop right out. So we should get x times the natural log of 4 is equal to 2x plus 1 times the natural log of 3. All we have to do now is solve for x. We need to get x by itself. Take a moment and look at this. It's a little tricky the first time you see it. It's nothing we haven't done since Algebra 1. It looks a little trickier because now we have natural logs. If we want to get the x's by themselves, all the x terms have to go to one side of the equation, all the other terms have to go to the other, and the best thing to do here is first distribute the right-hand side. I have x times the natural log of 4, therefore is equal to 2x times the natural log of 3 plus 1 times the natural log of 3. Now I can put my x terms together a little more easily. If I subtract on this side, x times the natural log of 4 minus 2x times the natural log of 3 is equal to the natural log of 3. Our goal is to solve for x. Our goal is to get x by itself, so let's start to isolate it here. What do we do if we want to isolate this x? X times, and think about everything here that x is being multiplied by, x times the natural log of 4 minus 2 times the natural log of 3 is therefore equal to the natural log of 3. And now I'm almost done. I have x times one big term. To get x by itself, I simply divide. X here is equal to the natural log of 3 divided by all of this, the natural log of 4 minus 2 natural log of 3. Let me say again what I said in a previous lecture. This is just a number. The natural log of 3 divided by 4 times 2 times the natural log of 3. It equals something. You maybe don't know exactly what it equals, but that's okay for now. Whatever it is something nice, and we can find it. Let's try another example. How about the natural log of the natural log of x is equal to 2. I now have x hidden inside of a natural log, and in fact that whole thing is itself hidden. Inside of a natural log, what do we do to free it? Well, remember how we undo natural log of x? We take e to the power of something. Those are inverse functions. That's the whole point of natural logs. It undoes e to the power of x. And so I can take e to the power of both sides. E to the power of the natural log of x is e to the power of 2. I know that e to the power of the natural log of anything is just that thing. So I have the natural log of x is equal to e to the 2, and now I just do it again. X is inside of natural log. E to the power of the left-hand side is equal to e to the power of the right-hand side, and therefore x is e to the 2. E to the 2 is a perfectly nice number. We can write it that way if we want. We might be happy to know this number is a little bit more than 1600. It's quite big. In fact, it's interesting, this function, the natural log of x, has a domain that goes up to infinity. If you let x get big, the natural log of x gets as big as you want it to. But it doesn't even pass 2 until x is 1600. In fact, it doesn't pass 4 until x is a 24-digit number. And if you wanted to pass 8, it would take a number with more digits than all computer printouts since the dawn of the computer age combined. This is a function that grows very, very slowly, yet it is a function. It's a nice function, and it's fun. So play with it. Let's now try two problems that look easy. Now that we're getting good at this, two related examples. E to the natural log of x equals 2, and e to the natural log of x equals negative 2. If you've been paying attention, you know that e to the power of and natural log cancel each other out. E to the power of the natural log of x is simply 2. E to the power of the natural log of x is simply x. The x comes down and is set equal to 2. What about over here? I would like to do the same thing, but be careful, be very, very careful. This is the tricky one. If I try it directly, I get x is equal to negative 2. Isn't that fine? Shouldn't e to the natural log of negative 2 be equal to 2? It's not. It can't be. It can't be for the simple reason that, think about what happens if we plug it in. What is e to the natural log of negative 2? It's nothing! There is no natural log of negative 2. You can't raise to any power, right? You can't raise e to any power and get negative 2. The domain of natural log, like the domain of every log, is only positive numbers. It's not permitted here. This is a false solution. It looks good, but it's not okay. And in fact, we learn a lesson here. When solving logarithmic equations, every time we think we found an x, we must go back to the beginning and plug it into the equation to see if it's okay. These false solutions are often called extraneous roots. Do you know this word extraneous? It's just a fancy word for extra. In fact, it's really just extra with some extraneous letters. Huh? Alright, fine. These are extra roots, these are extraneous roots, these are false solutions, these are things we can't actually use, and so we need to check these every time. We weren't careful for our first few problems, it turns out are fine, but from now on, every time we think we've solved something, we need to check. Let's see an example of that. In fact, let's look at a harder problem and try to find the roots of this. Solve the following ugly-looking equation. The base 4 log of x plus the base 4 log of x plus 3 is equal to 1. Somewhere out there in the wide world of real numbers, we hope there's some number x that will make this equation true. How then shall we find it? Stare at this equation for a little while. On the left side, you see the log of something plus the log of something, and we have good rules for this. We have properties of logarithms that let us combine them. We know this is the same as the base 4 log of the first term times the second term. This is the base 4 log of x times x plus 3. Must be equal to 1, which means that the base 4 log of x squared plus 3x must be equal to 1. We're closer, the problem looks easier, but it's still tricky. The x is still hidden inside of a logarithm we need to undo. How do I get rid of the log base 4? The base 4 logarithm? Well, the opposite of this. The inverse of this is 4 to the power of. If I take 4 to the power of both sides, 4 to the power of the base 4 log of x squared plus 3x is equal to 4 to the power of 1. 4 to the base 4 log of all this. Remember, these will cancel out. I'm left exactly with x squared plus 3x is equal to 4. And now we've taken a difficult problem about logarithms and turned it into an easy problem of the kind we're familiar with. We know how to solve this for x. We've known how to solve this for x since we took first year algebra. If I subtract 4 from both sides, I'm left with something that looks even more familiar, a quadratic expression that's equal to 0. This is a nice one. It turns out we can factor this as x plus 4 times x plus 1 equals 0. And the whole reason we do this, after all, the reason we solve these quadratic equations is this wonderful fact that if this first term times this second term is equal to 0, then one of those terms must be 0. Right? If you multiply a and b and you get 0, we know certainly either a is 0 or b is 0. It's one of our favorite things about multiplying. And so what must be true here? We must have x equals -4, or x equals, and let's see, this is -1.